So chapter 5 goes into something called vector components. And what vector components means is that when we're dealing with a vector at an angle, if we're dealing with something that's moving at an angle, that's being pulled at an angle, anything that's working at an angle, we've got to break it down into what we call vector components. Okay, so this is what we're going to talk about at the beginning of chapter 5, is something called vector components. Okay? And vector components is any time we have something at an angle. So this is any time we have motion or forces in more than one dimension. Okay, so what that means is that they are not just horizontal or vertical. This means we might be walking at an angle. We might be walking at 35 degrees north of west, right? We might be flying a plane 38 degrees south of east. Okay, all those kinds of things don't have just a vertical or a horizontal component. They have both. So we're going to talk about what it takes to break down these vector components, how we can build them together to find a resultant vector, to give us an overall sense of the motion. Okay, so can someone remind me what a resultant vector is? It's the sum of all vectors, right? The resultant vector is the sum of all of our vectors. So we're going to talk about resultant forces. We're going to talk about resultant vectors using velocity, using displacement. So we're going to take a little step back into working with velocity and displacement vectors again. But it all has to do with these vector components, okay, and things that move in more than one dimension. All right, so let's go ahead and review some trig functions because this section uses a lot of trig functions, okay? So here's my right triangle. I have sides A, B, and C, and I have angles A and B. Okay, let's say that this angle right here is 30 degrees, and let's say side B might be 10 kilometers. Okay, this is just an example. We're going to do lots of examples to help with our trig functions, but I want to see where we're at reviewing this. So what if I want to find side C here? Okay, if my goal is to find side C, I have an angle, I have one side, and I'm trying to find my hypotenuse, right? This is our hypotenuse side of the triangle. So if I have an angle and I have something adjacent to that angle, what trig function can I use to help find that hypotenuse? All right, let's write down all of our trig functions first, okay? Sine of theta is equal to what? Opposite over hypotenuse. Theta is our angle. Our angle always needs to be in degrees. That means our calculator always needs to be in degrees. So it's really, really important now for these chapters, especially for chapter 5, that your calculator is in degrees. So check that right now. Go to mode on your calculator, and it should be degrees, not radians. So scroll down until you see that. It needs to be in degrees. So if you're in pre-calc, you might have to make that switch when you come to this class. All right, what do we know about cosine? Cosine of theta is equal to adjacent over hypotenuse. And tangent is equal to, nope, opposite over adjacent. Opposite over adjacent. So you need to have these trig functions. If you don't have them memorized already, you need to get them memorized. Okay, because we will use these a lot. So now let's go back to our question here. If we were solving for if we were solving for side C, which would we use? We would use cosine, right? We have an angle, we have the adjacent side, and we want to find our hypotenuse. So this is how we plug that in. We would say cosine of 30, right, because 30 is our angle, is equal to the adjacent side, which is what? 10 over our hypotenuse, which is side C. That's what we're trying to find. How do I go about solving this algebraic equation now? I can switch these two places, which would give me C equals 10 over cosine of 30. Right? Whenever I have an equation that has three variables and the variable I'm solving for is on the bottom, I can switch those two places. So that means side C is equal to, what'd you have? 11.54. Okay. Let's try a few more with these trig functions. Any questions on this one, where these numbers came from? Okay. So here I have an angle that's 42 degrees. I've got a velocity vector of 38 meters per second. And I want to find this component, right? This now becomes a vertical component of this vector. So if this is my vector here, it has a horizontal component and a vertical component. So let's solve for the vertical component of that vector. Okay, which trig function will I be dealing with here? What do we think? Sine. Good, because I have my hypotenuse and I'm trying to find my opposite side. That side is opposite of my 42-degree angle. This side would be adjacent to my 42-degree angle. So I'm going to plug in sine of 42 equals question mark, or my opposite side over my hypotenuse, which is 38. Okay, so how mathematically do we go about solving for that? We're going to multiply by 38 on both sides. Okay, so you will see me a lot of times when we have to do this math, I'll just write 38 times sine of 42 equals that side that I want. Okay, because I'm going to take my hypotenuse times that trig function. Okay, so a lot of times I'll take out this step and I'll write it just like this. Okay? So 38 times sine of 42, what do we get for the vertical component of that vector? What'd you have? What would our units be here? Meters per second. Good. Okay, so let's talk about, this is a vector. This 38 meters per second is a vector. And let's think about just a car that's driving 38 meters per second at an angle of 42 degrees. Okay? What we're talking about here is that if we broke it down and we wanted to know exactly how far north they were traveling and how far east they were traveling, or what speed of each of those they were traveling, we would say they traveled 25.4 meters per second north, because we just found the vertical component of that vector. Okay, and we could find its horizontal component as well. Let's talk about cardinal directions, because we're going to have to use cardinal directions a lot to label our vectors and what angle they're moving at. Okay, so north, east, south, and west. All right, so let's say I'm leaving on some kind of a trip and I head out in this direction. Okay, and let's say I headed out at an angle of 18 degrees. All right, this angle right here, this 18 degrees, which axes is it touching? Is it touching the north axis, the east axis, south, or west axis? It's touching the north axis, okay? So from there, is it going west of north or east of north? Oh. Okay, so we want to find out what axes is it touching, and then from there is it going what direction? So this 18 degrees is 18 degrees west of north. Okay, the angle that we're looking at will always be touching an axis. So you decide what axis is it touching. We saw it was touching north. So from there it has to either go east or it has to either go west. Okay, and we saw from the diagram that it was going west. So we have an angle here that's 18 degrees west of north. Okay, some people can see it really quickly, south of east, east of south. Some people can't. So use that trick if you can't quite see it. All right, let's try another one here. Okay, so here's my 72-degree angle. What axis is it touching? It's touching the west axis. Is it north of west or south of west? So this angle is 72 degrees south of west. Okay, does that make sense? Okay. So I want you to try and draw a couple on your own. Let's say I want you to draw me a vector that is someone's walking 20 kilometers at 34 degrees east of north. Okay, and we're going to walk through how to do this because you're going to have to try to solve for this. So let's say I walk 20 kilometers east of north. The first thing that I'm going to do is draw my origin. Okay, I'm going to draw my axes. You can draw them big if you want. You can draw them small. It doesn't really make a difference. I usually keep them pretty small, but that's my axes. That's my starting point. Okay, that's my origin right there. The 20 kilometers, that's your hypotenuse. That's your vector that you're trying to look at the components for. Okay? We know we're going east of north, so our vector needs to go somewhere in this direction, right? It needs to go to the northeast somewhere. Okay, so we're going to go somewhere in that direction. Now, which axes would it be touching if it was east of north? It would be touching the north axis, so I'm going to draw my components. Usually your components are drawn in dotted lines. And where would my angle fit here in this triangle? In this angle right here or this angle? Bottom. Your angle should always be touching your origin, right? Because it's telling us where from our origin we're leaving. And then our 20 kilometers is our hypotenuse. So what this problem is telling us is that I'm leaving from my house and I'm going to walk for a distance or a displacement of 20 kilometers at an angle that's 34 degrees east of north. Okay? And what I would do with this information is I would be able to tell exactly how far north I traveled by solving for that side of the triangle, and I'd be able to find exactly how far east I traveled by finding that upper side of the triangle. Does that make sense? The overall goal of what we're doing here? Yeah or no? I want you to try this one on your own. I'm moving at a speed of 42 meters per second at 64 degrees west of south. Okay, so I want you to draw this system out, draw this vector out. If you're stuck, that's fine. Go ahead and take a look up here. If you're not, keep going. Start with your origin. You know it needs to go in the south and the west direction, so it's going to go somewhere down in this area. We know it's going to be touching the south axis, and it's going to the west. Okay, that means our angle should fit right in here, 64 degrees. And where does the 42 sit? It's the hypotenuse. Good. Okay, how many of you had diagrams that look just like that? Good. Good. Okay, so from there I want to take it a little bit step further. Okay, I want to ask you, this question might ask, find the vertical and horizontal components of this vector. The vertical and the horizontal components of this vector. So we would label this vector just V for vector or velocity or however you want to call it. If you've got multiple vectors, you'd label them as 1 or 2, right? We're only dealing with one vector here, so we don't have to label it 1 or 2. But this vector is going in this component. Is it our y component or our x component? It's our y component. Okay, so this is telling us we're dealing with a vector or a velocity vector. This is telling us it's our first vector, and that's telling us that's our y component of our first vector. Okay, so that's how we label the components. How would I label this side of that triangle then? V sub y2x. It's on the x-axis, that's right, but we're still only dealing with the first vector. This is one vector right here. We're only dealing with one vector, and each vector that's at an angle has 2 components to it. So this is still our first vector, and we're dealing with the x component of that vector. So we'd call it v sub 1x. Okay, the 1 tells us that we're breaking down that first vector that we got, which was this 42 meters per second at 64 degrees. Okay, so let's go ahead and solve for the components now of this vector. Right, if I wanted to solve for v sub 1y, okay, so v sub 1y, is it adjacent or opposite of my 64 degree angle? It is adjacent to the 64 degree angle. 64 degrees sits right here next to the origin. V sub 1y is adjacent to that angle. Okay, so I'd use which sine, cosine, or tangent? Cosine, right? I have my hypotenuse, I have my adjacent side, and I have my angle. So I would set it up like this. Cosine of 64, equals v sub 1y over 42. Right? 64 is our angle, or our theta. 42 is our hypotenuse side. V sub 1y is adjacent. Okay, so it could also look like this. 42 times cosine of 64. Right? All I'm doing is moving to that 42 to the other side of the equation. Yeah. 18.4 meters per second. Okay, because we broke down a velocity vector, meters per second, that means the units for our components must have a meters per second. They must also be velocities, right? Components are just 2 separate parts that make up this angled vector. Okay, and what direction is this y component going? North or south? It's going south, right? It's going in the south direction in order to make up that vector. Okay, so we would label that as a negative because it's going in that negative direction. Okay, so we say it's negative 18.4 meters per second. Let's solve now for v sub 1x. V sub 1x, we're going to use sine or cosine? We're going to use sine. So we'll say sine of 64 is equal to v sub 1x over 42, which also looks like this, 42 sine of 64. And you'll see me write it like this a lot, okay, just because it takes out one extra step. I got v sub 1x to equal 37.7. And what direction is this vector traveling? West, so it has to be negative as well. Once we've broken down this 42 meters per second at 64, we wouldn't use that again in the problem ever. Once we break that down into components, then we deal with the x and we deal with the y. Okay, we would deal with v sub 1x and v sub 1y. Once we break down that velocity vector, we're done with it overall. We want to deal with just the components. We want to deal with just x or just y. Okay, that's the whole goal. That's the whole reason we're breaking down these vectors into components, is to be able to use them separately. All right, so let's try some here, finding the resultant vector. Okay, so this is an example. Let's say I walk 15 kilometers west. And then I walk 20 kilometers north. What is my final displacement? Okay, and we're going to go through the whole process of how this works. We want to deal with these vectors individually. Okay, we're going to deal with these vectors individually. So go ahead and get the problem written down, and then we're going to work through these vectors. How many vectors are we dealing with here? How many? How many of you think we're dealing with one vector? How many of you think we're dealing with two? Okay, we have two vectors here. 15 kilometers west and 20 kilometers north. Our overall goal is to find one resultant vector. So if that's what you were thinking, that's fine. But our overall goal, yes, is to find one resultant vector. But we have two different vectors that are contributing to this resultant. Okay, we have two vectors that we have to take into consideration. So let's talk about our first vector, and we'll call this v sub 1. Okay, and I want to draw that vector out by itself. So v sub 1 goes 15 kilometers west. So this is all that my vector looks like. This is v sub 1. It's going 15 kilometers west. That's it. Is it going at an angle at all? No, because it's going straight west, so it doesn't have an angle. Okay, but we still want to find the components of that vector. So v sub 1 x is equal to, and v sub 1 y is equal to. We're going to break each of these vectors into its components. Okay, so if we look at this vector, if we look at our first vector here, we determine it's not at an angle, right? It's only going west, which means it only has which component? A vertical or a horizontal component? It only has a horizontal component. That means v sub 1y has to be 0, right? This vector is not traveling in the vertical direction at all, so it has no y component. Does that make sense to everybody? Okay. V sub 1x would be what value? Negative 15. That's perfect. Why negative? Because it's going to the west. Okay, that is really, really, really important. The negative here tells us direction, so we have to include that negative in our components. Okay, if it's going west or if it's going south, we have to include the negative. Okay, very good. So let's look at v sub 2 now. What's our second vector look like? Yep, going straight up. And what's the value of it? 20 kilometers. Okay, we're dealing with this 20 kilometers north vector. So if I look at v sub 2x and v sub 2y, I want to find the components of this vector. Does this vector have any horizontal components? Is it moving horizontally at all? No, so that means v sub 2x is 0. And what is v sub 2y equal to? Positive 20 or negative 20? Positive, very good. Okay. Do we understand why it's labeled like this, v sub 2x and v sub 2y? We're dealing with our second vector, and we want to find the components of that vector. Okay. So now, from there, we've got all of our vector components. We've got all of our x components and all of our y components. So now we're going to go ahead and start solving for our resultant. And the way we solve for our resultant is we're going to take v sub r for resultant in the x direction. And we're going to add up all of our x components. All of our x components. Okay, so our first x component, or v sub 1x, was equal to negative 15. What was the x component of our second vector? 0. Okay, so that means overall our resultant will have an x component of negative 15 kilometers. Okay, or 15 kilometers to the west. Our v sub ry, did our first vector have any y component? No. What about our second vector? Did it have a y component? Yes. Okay, so now we've got the components of our resultant vector. I know this seems like a lot of work for a simplistic problem, but I want you to understand the whole process because most problems will be much more complex than this. Okay? So we've got now the components of our resultant. So what we have to do is build now our new resultant triangle. We're going to build a new resultant based on these components. Okay, so I'm going to do that up here in the corner. Our resultant triangle, we're going to start with our origin. And we're going to just straight draw the resultant components. So what's the x component of our resultant vector need to look like? Yeah, 15 kilometers to the west. Okay, and our y component, or our vertical component of our resultant, needs to go 20 kilometers to the north. From there, I can draw my resultant now. I've drawn my components, v sub rx and v sub ry. And now this will give me an overall resultant vector. And how do I solve for v sub r of this triangle? Pythagorean theorem, that's right. Pythagorean theorem. Okay, so go ahead and solve Pythagorean theorem. You don't have to plug in the negative here when we solve for Pythagorean theorem. It's not going to make a difference because you square it anyway. But the negative tells us direction. So once you draw that, you're done with the negative. Okay, once you draw that new resultant triangle. Okay, so I got a resultant equal to 25. Okay, so v sub r is equal to 25 kilometers. We've got our magnitude of our resultant vector. What are we missing? We've got magnitude, but we don't have direction. So we need to solve for this angle as well. How do we solve for that angle? If we have the opposite side and we have the adjacent side. Tangent. Okay, so when we solve for an angle, we're taking tangent of theta equals opposite over adjacent. I gotta give myself some more room here, so I'm gonna get rid of some of this. Okay, so I know v sub r is equal to 25 kilometers. And when we solve for an angle, we're gonna take tangent of theta equals opposite over adjacent. So we know tangent of theta is equal to 20 over 15 because we want to find the angle from the origin. And what do we need to do in our calculator when we solve for an angle? you have to hit the second button. So you're going to go second tangent of 20 over 15, which equals 53.13 degrees. Okay, so we are almost done. We've almost got our full answer. We've got our magnitude, and we've got part of our direction. We know it's 53.13 degrees blank of blank. North of west. It's touching the west. It's touching the west axis. So is it north of west or is it south of west? North of west. The axis it's touching always goes second. Okay, where it's touching the west axis and it goes north of west, not south of west. Okay, so final answer is written at 25 kilometers at 53.13 degrees north of west. In here using components. So number 1 needs to be choose a coordinate system. That just means drawing your origin, understanding that north, east, south, and west look like that. That's what we talk about coordinate system. We always consider east and north to be the positive directions, south and west to be the negative directions. Okay, that's what coordinate system means. Okay, so number 2, step 2 is to be to break down each vector into components. Okay, that means taking each individual vector, whether they seem simple or not, and breaking them down into v sub 1x, v sub 1y, v sub 2x, v sub 2y, all that kind of stuff. Okay, breaking down each individual vector into x and y. After that, you're going to add or subtract your x direction. So add all components in the x direction. And add all components in the y direction. Doesn't matter what order you complete those in, right? You could do your y ones first. Okay, so in the y direction, that's when we solved v sub r equals v sub 1x plus v sub 2x, right? That's when we add all of our x components, then we added all of our y components. Use the new vector components to build a new resultant triangle. And then from there we use Pythagorean theorem to solve for hypotenuse. And second tangent, or tangent -1, to solve for angle. Sorry, I'm running out of room here. Okay, so that's step by step of everything we just did. We broke down our vectors into components. We added all the x's, added all of the y's. We used those new vector components to build a new triangle. Then we found the hypotenuse and we found the angle. What is the plane's final displacement? All right, so how many vectors are we working with here? 2 vectors. We have 2 vectors. Okay, our first vector we'll do in green. So here's our first vector right here. 500 kilometers at 65 degrees north of west. And our second vector we'll do in blue. Where's our second vector? What's our second vector? Perfect. 800 kilometers straight west. All right, so let's do V sub 1 first. I'm going to draw it out to see what it looks like. V sub 1 is 500 kilometers at 65 degrees north of west. So I'm going to start with my crosshairs and I'm going to draw the vector first so I can see what it looks like. Then we'll break it into components. Okay, so north of west means I need to go in this direction somewhere. Sorry, is that kind of hard to see? I'll move it over. Okay, it's north of west, which means it needs to touch the west axis and go north. And 65 sits in this angle right here. What's my hypotenuse of this? Yeah, 500 kilometers. Okay, because that's essentially my resultant of this component triangle. Okay, if I'm going to label this side, what am I going to label this side as? V sub 1x, perfect. Because it's my first vector and I'm dealing with the x component. I'm dealing with the horizontal component. That's why we say x and y. So this side right here, what would I call it? V sub 1y, very good. Okay, let's go ahead and solve for those. V sub 1x, I'm going to take my hypotenuse times sine or cosine? Cosine, good. Okay, and this is just another version of writing this. Cosine of 65 equals equals V sub 1x over 60. I can't write today, over 500. All I'm doing is moving the 500 to the other side and writing a shortened version up here. Okay, does that notation make sense to everybody like this? Okay. Do we agree on our component here? What are we missing though? A negative. Why do we have to include a negative here for V sub 1x? It's going to the west. So your math is not going to show you that. You have to look back after you solve for that component and decide, is it going north, east, south, or west? If it's going west or south, you have to add that negative. Okay? That makes a big difference. So V sub 1y, I'm going to take my hypotenuse times sine of 65. And I got 453.15 kilometers. Do we need a positive or a negative for that one? Positive, because it's going north. It's going in the upward direction. Negative 800. Why is it negative? It's going west, right? Does V sub 2 have any y component? No. So V sub 2y is equal to 0. Okay, so if you look at the steps we've done, out of our steps for solving vector components, we've done number 1, choose a coordinate system. You can check that. We've solved vectors into their individual components. Done that. Okay, our next step is to add the vectors in the x direction. Add all components in the x direction. All right, so let's start looking at our resultant vector here. Okay, so v sub rx is equal to v sub 1x plus v sub 2x, which equals negative 211.31 plus negative 800. Why do we need negatives for both of those vector components? They're both going west. Yeah, they're both going west. Okay, so there's our v sub rx. Do we all agree with that? Okay, now let's solve for v sub ry. I'm going to give myself some more room up here. We're going to take v sub 1y plus v sub 2y, which is going to equal, what's my v sub 1y? 453.15. V sub 2y was equal to 0, which means v sub r, my resultant vertical component, is equal to 453.15 kilometers, and it's going north or south? North. Okay, so it stays positive. So you can give yourself a little arrow if you want, just to remind you about direction. You don't have to do that, just gives you a good idea. Okay, so now we've done add or subtract our vectors in the x and the y direction. We're going to use the vector components to build a new triangle. So that means we're going to look at v sub r, and we're going to build a new triangle. So here's my origin here. My x component needs to go east or west? Needs to go west because it's a negative. That negative right there tells us that our x component needs to go to the west. Okay, and that's going to be labeled 1011.31. My v sub ry needs to go in the positive or the negative direction? Positive. So it's going to go positive. And that value is 453.15 because that's what I solved for. So I used those v sub rx and v sub ry to build a new resultant triangle. And now I'm going to look at the hypotenuse to equal v sub r. So we need to find hypotenuse using Pythagorean theorem, and we need to find the angle using second tangent. Here I want your full answer. I want the magnitude and the direction of this vector, of its resultant. And what this is going to tell us is going to tell us exactly how far this plane is from where it started. Okay, even though it took kind of a jagged path to get there, we're going to look at exactly how far it ended up from where it started. Or something close to that? 1108.2? For my magnitude? Do we not agree with that?
I agree.
Okay. Go ahead and solve for our angles now. So we're going to use second tangent. Our opposite side is 453.15. Our adjacent side is 1011.31. Good. 1108.2 kilometers at 24 degrees north of west. That's our final answer.